Hello and welcome to the Juniper Networks Learning Bytes series. I'm Josh McKenzie, a content developer here at Juniper Networks Education Services. And today we're going to be doing a bit of an introduction to Kubernetes. So when we're done here today, you will have learned the purpose and application of the Kubernetes orchestrator, some of the most common abstractions managed in Kubernetes, and how to deploy a very simple containerized application in Kubernetes. To understand Kubernetes and why it's such a big deal, we really need to understand the promises and pitfalls of microservices. So modern applications tend to break up all of the processes involved in actually providing a service into their individual constituent parts, which are managed separately. These are our microservices. Now, this approach can really simplify things from a developer's perspective because you have all of these components with common interfaces. Developers can update the individual components without having to worry about updating the entire stack, provided that those interfaces, those APIs between those components remain constant. This also means each component can run where it runs best. So different hardware might be optimized for different components of our application. For instance, this natural learning or natural language processing API here, probably going to have very different hardware needs than, say, our SQL database or our time series database. This also, by shrinking down the scope of direct effects changes can help us get to faster release cadences so we can get new features online more quickly. Now, at the same time, we want our services to still seem simple from the perspective of our end users. And creating that simplicity is actually inherently complex. We're managing a large number of components that now have desynced release cadences. Those components are going to have different scaling needs. They're going to have different reliability and resiliency constraints. So we are now dealing with microservices components that are both independent and yet at the same time interdependent when it comes down to actually providing a service to our end users. So this is a little bit like an orchestra. So if you think about an orchestra, it's dozens and dozens of talented musicians playing carefully tuned instruments. Those are sort of like our developers working on each of the individual components for which they're responsible. However, in order to actually produce good music, all of that talent in tuning is going to go to waste without some coordination. We need some system to actually tie all these parts together and make sure they run smoothly as a whole. So just as an orchestra needs a conductor to ensure that all of these finely tuned parts actually work together as a finely tuned whole, our microservices applications need an orchestrator. So this brings us to Kubernetes. So Kubernetes is an open source container orchestration system developed by Google. It uses a declarative configuration. So this is an example of infrastructure as code. So we write our resource definitions, which are called manifests, typically in YAML, although JSON is also an option, and then rely on Kubernetes to turn those representations of our infrastructure into realized services. Kubernetes is very flexible. It uses a pluggable framework called the Container Network Interface to give us a lot of options for how we want to implement the actual network portion of our infrastructure. This is where tools like Contrail actually integrate with Kubernetes. The whole platform is designed to be extensible and hyper-scaling. This was developed by Google after all, so any scale you could possibly need, Kubernetes can handle. It also has some of the key features you are going to want if you are looking to deploy microservices at scale, including auto-scaling, self-healing, load balancing, and service discovery. Here we can see what the Kubernetes architecture actually looks like. This is straight from the Kubernetes documentation. So you can look first at our nodes. In this case, we have a 3-node Kubernetes cluster. So any group of Kubernetes nodes that are managed as one unit, we're going to call a cluster. And there are 2 key processes that run on each of these worker nodes. We have the kubelet, which is responsible for actually managing our containers by interfacing with our container runtime. Typically, this is Docker, although it does not have to be Docker. And then the kube proxy, which is responsible for handling the networking component of Kubernetes. In the control plane, we have a etcd database. This stores all of the Kubernetes state data. The Kube API server is really the central management point of the Kubernetes control plane. This is what issues requests to the kubelet and kube proxy processes on each Kubernetes worker node. It also interfaces with the scheduler, and the scheduler does the work of coordinating where containers are actually provisioned. So when we tell Kubernetes, hey, I want 10 replicas of this container, it decides where they actually get created across our nodes. Let's talk about some of the objects that are managed in the Kubernetes API. This is far from an exhaustive discussion. We are just going to cover the most fundamental objects you're going to work with in Kubernetes, starting with a pod. A pod is the smallest service unit Kubernetes manages. Typically, a pod represents a single container, but it can also be several tightly coupled containers. What's critical here is that all of the containers within a pod are always deployed on the same node and assigned to one shared IP. So typically, we don't want our services to be so tightly coupled that they need to be on the same hardware, but there will be some specific cases where we might have multiple containers in a pod. But for most applications, you can consider a pod to be a container. A service is a logical group of pods that are exposed as a network service with a virtual service IP. So if I have 100 replicas of a particular container and I want to load balance requests across those replicas, I'm going to need a service to do that. So that's the primary thing a service is going to do. It can provide load balancing between those pod replicas. In other words, it enables horizontal scale. There are several flavors of services. We're just going to briefly talk about the most common ones. So a cluster IP service exposes the service on an IP that's reachable by other pods within the cluster. So this is not going to be reachable outside of the local cluster. So if we have services that are only used by other services within the cluster, a cluster IP might be appropriate. The node port service exposes the service on each worker's node IP using port mapping. This can be useful in test and lab environments. Most of the time, we're going to use the load balancer service type. This exposes the service externally, in other words, publicly, using a cloud provider's load balancer. So this could be AWS, Google Cloud, as we're going to use in our example, Azure, or whatever cloud provider service you're actually using to host your Kubernetes nodes. Last, I want to talk about ReplicaSets and deployments. So a replica set ensures that a specified number of pod replicas are running at any given time. So once we deploy a replica set, the Kube scheduler is going to monitor existing replicas of that pod and initialize new replicas or stop existing ones to ensure that the desired replica count is maintained. They can also specify the required properties of nodes running the replicas. So if our pods run best on a certain type of node, maybe a CPU optimized node or a memory optimized node, we can include that in the replica set definition. There's also a related object, which we're not going to work with today, but is worth understanding, called a daemon set that can ensure that a single replica of a pod is running on every node. So if there's a particular service that needs to run on every single node within our cluster, we would want to use a daemon set to do that. And then lastly, we have deployments. So a deployment is a high-level abstraction that actually allows us to manage several other components, specifically pods and replica sets. And what's really critical about deployments is that they provide us with simple declarative updates for pods, which are then managed by replica sets. So this allows us to manage the scale up, or I guess scale out, and scale down processes. This also supports features that are going to be really important in CI/CD environments, like rolling updates and canary deployments, where we can deploy application updates in a manner that ensures that our overall scaling doesn't change. So as old versions of our containers are torn down, new ones are built up at the same time to ensure we have the same number of replicas available at any given time. Or canary deployments, where we can actually deploy an updated container image to just a subset of our users or a subset of our nodes. Our recommended best practice here for managing pods is generally going to be to use deployments to manage replica sets and in turn pods, rather than managing and creating them directly, because there's a lot of power in this deployment object, as we're going to see in our demo. So for our demonstration, we have set up a 3-node Kubernetes cluster. We can use the kubectl CLI tool to view and manage this cluster. So we'll start by running get nodes to see the nodes that are part of our Kubernetes cluster. So as you can see, we have 3 nodes currently running. These names are automatically generated by the Google Kubernetes engine. We'll cover actually setting up Kubernetes clusters in the Google Kubernetes engine in a later video. For now, we'll just treat this like any other Kubernetes cluster. We can check for currently running pods with kubectl get pods and see that there's nothing found in the default namespace. There is a system namespace, which contains all the actual system components, but currently we have no user pods running. We can also check for certain deployments and services. You can see the only service currently running is the Kubernetes control plane service. So pretty much a clean slate to start with. So what we're going to do is create a very simple web application and then deploy it using a deployment. So first, let's take a look at our source code. In this case, we're using a simple web server written in Go. Not crucial that you understand Go for this example, but what this server is going to do is simply respond to requests with hello world and then the name of the host, the actual host name specific to the container that's servicing the request. And that's going to allow us to see the load balancing in action. You can see our Docker file here, just defining the basic parameters to run this. We have a previous learning bite covering how Docker files work, so we're not going to spend much time on this. What we're interested in today is our actual deployment definition. So this file, godeployment.yaml, actually defines 2 API objects. We're defining a deployment and then a service, which is going to expose that deployment behind a load balancer. You can see the 3 lines indicate the start of a new YAML object. So we have 2 objects here. We'll look first at the deployment. So the Google documentation for this is really excellent. If you really want to start building your own Kubernetes objects, I highly recommend just starting with the Google Docs. We're going to talk about what each of these statements mean for our specific deployment, but obviously we're not covering all of the options available. So the first key you need to define in your manifest is the API version. So this is going to be the application API version 1. Then the kind. This is specifying what type of object this is. In this case, we're defining a deployment object. Every object in Kubernetes can be assigned metadata, starting with the name, and then any labels we want to attach. And these labels can be used later on by other objects that want to reference this deployment. Then under spec, this is our deployment specification. We first define how many replicas we want to deploy. Let's say 5 replicas. Then we have the selector. So the selector allows us to define a deployment to manage a pod that might already exist. And we're going to do that by matching on label values. So we're going to match on labels. Specifically, we're looking for a label called app with the value of Go server. Then in our template, that's where that label is actually created. So under our template metadata, we're labeling our template with the app called Go server. So this spec for the deployment is going to make sure that there are 5 replicas of this template with this value, with the Go server on the app tag. Then in the spec for the template, we define our containers. Worth noting, each one of these objects can be created separately. We're just doing them all together inside of this deployment. So this particular template has just a single container. Notice this is a YAML sequence. We need to define the name for that container, the image. So in this example, I've already run a Docker build against this Docker file and uploaded this container to the public Docker Hub. and then ports I want to expose on that container. And I'll use the container port directive to do that. So we're going to expose port 8080, which is what my web server is going to be trying to listen on. So that's going to create my deployment. In the same file, I can also expose that deployment using a service. So we have the version 1 for the API version. Now for this manifest, the kind is service. We're going to have just the name metadata here. We're going to call this Go Web Service. Then in the spec or specification, we define the type. This is going to be load balancer. So how that load balancer is actually implemented is going to depend on where I deploy this service. In this case, I'm deploying it on the Google Cloud platform, so I'm going to use their built-in cloud load balancer. It makes things really easy for me if I'm looking to manage this application. I don't have to deal with provisioning and managing my own load balancer. The cloud takes care of that for me. For my selector, it's going to load balance between all pods that match this value, where the app tag equals Go server. That's going to match these pods right here. Then I define my port mapping. So this is going to be protocol TCP. I'm going to map port 80 on the public IP this is going to create to port 8080 on my container. Now, this 36-line YAML document is all I need to spin up those containers, organize them into a replica set, and then expose that and load balance across all of those replicas at a public IP automatically created for me by my cloud platform. Pretty darn cool. So let's go ahead and run this. So run kube control, apply, and then specify the file. And that's it. So it's going to create my deployment. Inside of that deployment, it's creating each of those pods as well as a replica set to contain them. And then I'll define the service to expose those. So if I run kube control get pods, you can see I have 3 pods here. I guess I forgot to save my file with the updated replica count. That's fine. We'll actually scale it up in a minute. So we've got 3 replicas. For on kube control get deployments, you can see I have a deployment with 3 of 3 containers. I can also see that even though I didn't explicitly define a replica set, one is actually created by that deployment. And if I run kube control get services, you can see the load balancer service created as a result of that manifest file. I can also see both the cluster internal IP and the external IP for that service. Now I can test that service just by trying to reach my application at that public IP. So you can see my first response is telling me there's my hello world, and it's telling me the name of my host. I can verify if I do get nodes that that is, oh, not get host. I can verify if I run get pods, that's coming from this pod right here. And if I keep issuing that curl command, you can see each request is being serviced by a different container. So it's being load balanced across those replicas. And sometimes we'll get the same one repeatedly. Now, let's say instead of just 3 replicas, I want 10 replicas. So I forgot to save this change before anyway, but let's go ahead and change it to 10. We'll save that. Now, to scale out this application from 3 replicas to 10 replicas, I just have to apply that file again. And Kubernetes will automatically take care of the work of adding new replicas and adding those to my load balancer configuration as they're provisioned. So if we do get pods, you can now see, and one is still creating, but now I have 10 replicas. And if I try to issue a request to the load balancer, it's now being load balanced across all 10 of those replicas. Thank you for joining me for this Learning Bite. I hope you found this useful. If you'd like to see more like this, please subscribe to the channel, and I'll see you next time.
Visit the Juniper Education Services website to learn more about courses. View our full range of classroom, online, and e-learning courses, learning paths, industry segment and technology-specific training paths. Juniper Networks Certification Program, the ultimate demonstration of your competence. And the training community, from forums to social media. Join the discussion.